Yeah. All right. So let me begin by thanking ICTS for organizing this meeting, and then for Shamriddhi for doing all the hard work. Okay. And what I will talk about today is particles and fields in superfluid turbulence. Okay. Some studies that we have carried out. Who is we in this? We is really Vishwanath Shukla, who has done all this work for his PhD. He's now a postdoc at the École Normale in Paris, and Marc-Étienne Praché, and we have been funded by various organizations, especially IFCAM, which is the Indo-French Center for Applied Mathematics. So Marc has been visiting, and the other way around under that. Okay, so the work is based on several papers, some published, some not published, some to be submitted, etc. Turbulence, all of you know, but it's not clear that the normal view of fluid turbulence is applicable to superfluid turbulence. So here I follow one of the recent reviews in this area. So it's a dynamic field, spatially complex, aperiodic in time, spanning several orders of magnitude in spatial extent and temporal frequency. It's produced in many ways. There are many experiments. Some of them you saw in Itamar's talk. So this is an old one produced between two counter-rotating disks. It can be done. You can move a grid steadily through a superfluid, and you can study reconnection of quantized vortices. You can look at velocity statistics, many things, all of which I won't cover. A new setting, it has also been observed in Bose-Einstein condensates of alkali atoms, for example, of rubidium-87, by applying some external oscillatory perturbation, and you can get turbulence here too. And of some relevance to my talk, you can also get two-dimensional quantum turbulence, because as you will see, at least in this talk, I will concentrate on two-dimensional superfluid turbulence. So there are at least three levels of description for a superfluid. One is the Gross-Pitaevsky level, which is good at very low temperatures for a weakly interacting Bose gas. And this accounts for phenomena at the length scale of the superfluid vortex core. Then there is a vortex filament model, which distinguishes between individual vortex lines. You saw some of this in Itamar's talk. It ignores the nature of the vortex core, and it is valid at length scales greater than this vortex core length. And if you become even more coarse-grained than that, there is so-called two-fluid Hall-Vienen-Becharevich-Khalatnikov model. This does not distinguish between individual vortices. You have a continuum vorticity field, and it does require certain special alignment. I will make that clear as I go along. So let me begin with the first thing we did, which is turbulence in the two-dimensional Fourier truncated Gross-Pitaevsky equation. That's a mouthful. So let me tell you what that means. This you probably know. This is a standard Gross-Pitaevsky Hamiltonian, and then associated with this is this Gross-Pitaevsky equation, where psi is the macroscopic sort of wave function of the Bose gas. G is the interaction strength, and since we are in two dimensions, L squared will be the area of the periodic domain. And this thing conserves the energy, which can be written like this, and the number of particles. Okay. There is this famous Madelung's transformation. You do this, so that's the amplitude, that's the phase. The velocity is related to the gradient of this phase. So this is the velocity of the superfluid. There's an equation of continuity, and you can write down something for theta 2. And if you now look at wave propagation, this is all history. There's nothing new about it. So you can get a Bogoliubov dispersion relation. There is a speed of sound. There's a healing length, which will set the scale of the vortex core. Now, this sort of superfluid flow is irrotational, so curl V is 0, except at vortices that are zeros of psi. The topological defects, circulation is quantized, and rho goes to quadratically in R as you approach a vortex core. So again, that's the energy. If you write it in this fluid sort of variable, you can separate it into a kinetic energy, an interaction energy, which has to do with this, and this term is traditionally called the quantum pressure energy. And then you can take this and separate it into compressible and incompressible parts. So you take rho to the 1/2 v, to write it like this, and this part has divergence 0, this part has curl 0, and at the end of the day you can then separate it into incompressible and compressible parts to touch base with conventional fluid turbulence. So given those energies, you can then do Fourier transforms, and in terms of those you can look at various energy spectra: incompressible, compressible, interaction, quantum pressure, and you can also look at occupation number spectra, where the hat over these symbols indicates Fourier transforms. Okay, occasionally we will have to use the stochastic Ginzburg-Landau equation to inject some sort of temperature into the system in a way which I will not describe very precisely, at least in my talk, but if you're interested I can tell you later. So this is just basically to define things, that standard Ginzburg-Landau, and there's a noise, etc., and so on. Okay, what do I mean by Fourier truncation or Galerkin truncation? Anybody who does pseudospectral codes, we could have taken the original Gross-Pitevsky equation, done a Fourier transform over space, and then schematically the equation of motion for this Fourier component would have been this, and that's some complicated nonlinear function. In any practical calculation, all modes with the moduli of the wave vector greater than k max are set equal to 0. So that gives you some number of Fourier modes. So nc squared, let us say, number of collocation points if you want to sound applied mathematical. Now, okay, so then we are solving a finite dimensional dynamical system, if you will, because got however many modes there are. So you can ask how well is the solution of the partial differential equation satisfied by this. It's okay where if you have what's called spectral convergence, but doesn't matter. But for this part of the talk, we are going to take these equations truncated in this sense, truncated in Fourier space. So we have a finite dimensional Hamiltonian system of ordinary differential equations. And of course, energy is conserved. So if you like, we are working in the microcanonical ensemble. And if we inject some stochastic Ginzburg-Landau, we can make it grand canonical. Let's not worry about it. So of course, all the statistical mechanisms in the audience, sometimes if I give this talk to fluid dynamicists, then I have to explain more. But all of you will know that eventually this must equilibrate. And if and when it equilibrates, then this is 2 dimensions, so you should get a Berezinski-Kosterlitz-Thouless phase characterized by that correlation function. Excuse me. Below this transition, there will be an algebraic decay of this correlation function. Above it, exponential decay, and so on. So if you're doing the simulation microcanonical style, then this will be controlled by the energy. All right, so what did we learn that other people didn't know already? Well, bits and pieces were known. Certainly, Berezinski-Kosterlitz-Thouless has been known for years. But it turns out there are lots of different simulations all over the place, some done by statistical mechanicians, which have only concentrated on this. Then there are some done by people who come from a fluid dynamics background. So they have looked at basically either the beginnings or all the way of thermalization. I would like to believe that we have studied thermalization in this system, which is the truncated 2-dimensional Gross-Pitevsky equation. And when we do this, we find, roughly speaking, 4 dynamical regions. There's initial transients first, and not surprisingly, they depend on initial conditions. Then there is the onset of thermalization. You begin to see power laws, but they don't last very long because the system is changing. Many people have claimed that they have seen Kolmogorov-like power laws in energy spectra. Okay, either they've done it in a slightly different system in which they put some artificial dissipation into the Gross-Pidevsky, or they're concentrating on a very tiny region in time where you see some power laws. Then we see a region of partial thermalization where there is some universal behavior which I'll tell you about. And then there is something which we've been calling self-truncation in spectra, which is sufficiently technical that I will explain it with some figures. And then of course there's Berezinski, Kostler-Saulis. As I said, I know no study which has actually progressed through all these states. So let's begin. We've done it for many different initial conditions. Please don't worry about it. This is only for super experts. But this is to tell you that the answers, at least qualitatively, do not depend on initial conditions. So we've done many runs. The the resolution might not look wonderful, but we have explored huge amounts of parameter space. So that's the main reason why we have limited the resolution with a view to exploring parameter space and initial conditions to explore how this system thermalizes. Okay. All right, so I will now show you a movie which shows you how thermalization occurs. The first panel here will be a probability distribution function of any of the velocity components. You will note already that it seems to have a power law tail, roughly 1 over v cubed, which is supposed to be the signature of quantum turbulence. People, got papers into PRL saying this. As we will see, this happens in the beginning, but as vortices disappear, it goes away. There is a pseudo-color plot of the vorticity that will show you how the vorticity evolves. Here are spectra. Okay, you can't see all the details, but the brown line is the kinetic energy, incompressible, compressible, quantum plus the interaction and so on. So you will see how they evolve, and this is the occupation number spectrum. There is a dashed line here which tells you what the form should be when the system finally thermalizes. So if you watch the time evolution now, you will see how it goes towards thermalization. Okay, it'll just take a second. With some luck, it will work. All right, there we go. So you see initially, you see this 1 over v cubed tail. There are vortices around. That's how the spectrum is evolving. Some part is thermalizing over here. It's already changed. No vortices left. It's become more or less Gaussian as it is in conventional turbulence, but for a slightly different reason. Here it's thermalization. You can see this part of the spectrum is becoming linear. I won't play it again. All right. Now, let me show you one characteristic. Here is a schematic plot of the energy spectrum. And you know that it had a part which was showing the thermalized behavior and then falling off. So there is over here some sort of a dynamically generated cutoff, a self-truncation vector k sub c, which is significantly lower than the k max, the k at which we are truncating the system. You can estimate this in many ways. Don't look at the details. So how does the system evolve? Eventually, this kc should go out all the way to k max for the system to thermalize. And we find that there are two possibilities, many possibilities, that it goes with a power law, and there is a prediction for that power based on wave turbulence theories. They predict 0.25, but what we have shown is that you can get anything from 0.25 to basically 0, that is logarithmically slow growth of kc if you do that. We have looked at many other dependencies, like dependencies on g number of things and so on, but eventually we can cook up special initial conditions for which this Kc goes very slowly. So here is a plot over several different runs. I just want you to concentrate on this one column here. That is the power alpha with which this self-truncation vector goes out towards K max. And for some things it is around 0.25, which is the wave turbulence prediction, but it is easy enough to find initial conditions for which it goes very slowly, and so the wave turbulence prediction does not apply in all cases. You can ask, well, can you ever go to thermalization fully? We can, especially if we keep the system size down. So here you see the spectrum going linearly with K. It's linear with K because we are in 2 dimensions. In 3 dimensions that would be K squared. All right, and then do we find costless Thouless? I would like to believe that we have done this most carefully, and yes, if you are at sufficiently low temperatures you find costless Thouless phase, otherwise you don't, with all the right the right exponents, that is an eta of 0.25 for those who know such things, but that's not important. And above it there are always vortices that are present, and therefore you get a PDF which has this 1 over v cubed tail, roughly 1 over v cubed that I told you about. So this is just a repetition of what I said. Let me now go to a case where we are not looking at thermalization, but where we are looking at the interaction of particles with this Gross-Pideevsky field. So why should you bother? Well, you should bother because experimentalists, you saw these pictures in Itamar's talk, are using these particles, often say solid hydrogen or deuterium, to track these vortices. And these particles are actually much bigger than the size of the vortex core, yet they seem to be able to track it. So let's write down a model where we can actually look at the interactions of the particles with the field and the effect of the field on the particles. So this part of the talk will look at how the particles are affected by the superfluid turbulence and how they in turn affect the superfluid turbulence. So it's back to Gross-Pideevsky, probably in slightly different units. Please forgive me, we change units from one paper to the other. This P sub G is the projection, the Galerkin truncation projector. This is just chemical potential, and that's the particles. So we allow for N0 particles. So there's a potential which you can impose. I will give you the form of the potential. It's basically a Gaussian. So there's a sum over n naught Gaussians, all right? And there's Newtonian dynamics for the particle. It's sufficiently large that we don't have to worry beyond Newton, okay? And there are 3 forces that we have. One is the force that the fluid puts in the particle, superfluid, excuse me. Here is an external force that I might choose to put on the particle, and finally we put in a short range repulsion between particles, because if you don't have it you get some effects which I will tell you about as we go along. So it's only Gross-Pideevsky plus a particle, okay? Now has such a model never been written down before? Well, it has been written down to some extent. I think Adams did some calculations in 3D with the same thing, except he didn't have a short range repulsion, which is very important if you look at interactions between particles in such a superfluid. So just for the sake of completeness, I am giving you the force exerted by the fluid on the particle, which is related to the gradient of this particle potential, which can be written in some nice way, but don't worry about the algebra. So the energy has 3 components. One is the energy in the field, which is here. Then there is the kinetic energy of the particles. And then there's a short range repulsion energy, which we need when we have more than one particle. This is sort of like the hard core in a Leonard-Jones. So actually we use a 1 over r to the 12. And so there are some parameters here for the short range thing. Delta E is the strength of it, and RSR is the thing with which we scale the R. So by changing these we can change the the interaction between the particles. So here's the total momentum and the number of bosons, and these are conserved by the dynamics. And that's the particle potential. So for any one particle, you have a sort of Gaussian, okay, and the dp over here is the control parameter for the particle size. Now when you put a particle inside the superfluid, let mf, little mf, be the mass of the displaced superfluid. Then the particle has mass m naught, and then that gives you a dimensionless ratio, script m. If this is much greater than 1, we will say the particle is heavy. If it's 1, we'll call it neutral. If it is less than 1, we'll call it light. And you will see different interesting behaviors as we go along. Numerical method is the same, pseudospectral, etc., etc. Okay, this is something which is only for super experts, so I won't tell you about it. All I want to tell you is, given this bit of numerical technology which has been developed by the group of Marc-Etienne Brachet, we can generate, you see, now we have a compressible flow because I separated it into compressible and incompressible parts. So by preparing initial conditions by this level of trick, then we can start with initial conditions where there are hardly any sound waves. Then as particles are accelerated, churn, collide, they will generate sound waves, which you will see. So it becomes easier to, So we've done many simulations. I won't bother you too much with all of them except some illustrative ones. I will show you a vortex pair being shed from a single particle. That's not new, that's been done before. But I'll show you some interesting two-particle dynamics and many-particle dynamics and so on. Okay, so what do we do here? We have a heavy particle and we are just pulling it through the fluid with a given force, okay, a constant force. And let's look at the spatiotemporal evolution. At the moment nothing happens, so let me speed it up a bit. So around here something interesting will happen. When it crosses this critical velocity, it shoots off those vortex pairs, vortex anti-vortex pairs, and then it churns up the whole fluid. So the particles and the vortices interact to give you a really turbulent superfluid. Okay? Color is the rho, so that you see, yeah, right. So you see the sound waves because of that. And then the particle is the blue. Now if you did it with neutral particles, you'd get something slightly different and so on. Let me not do all the details. Instead, let us look at the plots that emerge from this. So let's look at just velocity versus time. So these maxima and the velocity occur near the critical velocity, which has been known for several years. And when it goes to this maximum, it shoots off a vortex anti-vortex pair. But then it sort of responds in some way. If you look at this, it's actually periodic for the neutral case and more complicated than periodic for the light case. You can Fourier analyze and you can see that there's very little background turbulence, but there's enough to give some periodic motion to the particle after it has shot off those vortex pairs. And if it's light, it's actually chaotic. I mean, the motion of the light particle in this fluid is chaotic. Okay? Again, I think this has never been characterized before. Now let's look at two particles. If you just take two particles with no repulsion between them, they will actually come together and form a sort of bound state and keep on oscillating. Why does that happen? Well, you can actually derive it, roughly speaking, from the Gross-Pietaevsky equations by doing some sort of approximation, okay? But let me not do that. Let me just show you here a plot of the displacement. So the two particles come together. Green is one and purple is the other, and you can see this, they come together and they sort of form a bound state where they oscillate. But if you put in a short range repulsion, then they go away, okay, they rebound, all right? So let's try to characterize this. I mean, you can actually calculate the effective interaction between these two particles, which is attractive. But now let's put in a short range repulsion and make two particles collide. Okay? So we look at a head-on collision. There are two particles, they're accelerated towards each other, and then you turn off the force at some, at some time here, and then let's see what happens. Okay? So first let's look at small values of this short range repulsion, and this is what you will see. The particles will come together and they will hit and generate lots of sound waves, but still the repulsion is not strong enough to push them out. Okay? So let's see what happens if you have a stronger repulsion. Particles come together. This is like Resnick and Halliday. Huh? This is head-on collision. Okay, they rebound. All right? But it's Resnick and Halliday with the things embedded in a superfluid. So, okay, so superfluid affects the flow and so on. Now, you can look at how the energy is exchanged between the components. And if you look at that, you will see that the first collision was more or less inelastic. And as you increase the repulsion, it became elastic. So you can write down a coefficient of restitution. I mean, Itamar talked about coefficient of restitution in his talk on bulk metallic glasses. He had a ball, bulk metallic glass bouncing. So here we have two particles in a superfluid. If the repulsion is not very strong, it's completely inelastic. And there comes a time when the repulsion is strong where it becomes elastic. As far as we can tell, this is a continuous transition. But you know, the error bars are large, so we can't give you an exponent. As far as I know, this has never been noted before. And you can scan through this transition not only by changing the strength of the interaction. If you hold the interaction strength fixed and change the mass from light to heavy, again, you will see this sort of a transition. This should certainly be measured, and this, I'm willing to bet, is not affected by 2 and 3 dimensions. The same thing will happen in 3 dimensions. Okay, so let me show you a little more complicated thing. After all, we are after turbulence, so let's see. By the way, this is to people who do particles in turbulence. These are active particles. What's it called? Two-way coupling. Particle acts on the superfluid, superfluid acts back on the particle. So it's quite complicated. It's not trivial calculation, right? So this, we'll start off particles like this, okay, and in the case where the repulsion is weak, you will see they'll come, generate lots of sound and get stuck, all right. So, but if it is strong, the repulsion, okay, they'll rebound, and because of periodic boundary conditions, they'll keep on rebounding. But then all this turbulence will introduce some little bit of asymmetry, so eventually it'll move off. And once it moves off, okay, everything is turbulent now. If you analyze the motion of the centers of masses of these particles, they're chaotic. The fluid is certainly turbulent by the criteria I gave you earlier. That is, it's churned up at all scales. There are a large range of spatial scales, a large range of time scales. Okay, so we can keep on watching movies. Let me just show you one more or something. All right, so this is a vortex pair and 2 particle interaction. Okay, so okay, yeah, here. Okay, let's see what this is. Okay, this is one particle with some counter-rotating. Let me just start this here because this will lead me into the next part of the talk. Look at the initial condition. There are clusters of vortices of one sign, and there's this little Mark calls this Pac-Man, okay, eating up these vortices, and slowly it'll go on. So here is, if you like, again, interaction of particles and fields and vortices in a turbulent superfluid. Okay, let me just show you one more. Suppose you start this like this. So you start with these particles and counter-rotating vortices. Okay, we can start a film company or something here. Huh? No, but it's interesting. I want to show you something. See, now it breaks. Now these particles seem to be executing some sort of periodic motion. It's not quite periodic. You can actually characterize it by using all sorts of Fourier and whatnot. But if you, for example, trace the centers of masses of these particles, they are not moving on a fixed curve. They're actually filling up some area. I think if you track it carefully enough, it is quasi-periodic, which I won't tell you. Okay. So here's a summary of this 1/3 of the talk, that particles in fields and superfluids. The particle motion can be chaotic even if the superfluid shows very few signs of turbulence. Vortex motion depends sensitively on particle characteristics. There is an effective superfluid mediated attractive interaction between particles. If to this you add a short range repulsion, you get very nice possibilities. You can scan through a transition from inelastic to elastic collisions, and if you have assemblies of particles and vortices, you get very rich turbulent spatio-temporal evolution. Okay. Now the last part of my talk has to do with these whole Winen-Bekarevich Khalatnikov equations. Okay. So if you go to a typical solid state physicist and say, I'm working on superfluid turbulence and I'm using Gross-Pidevsky, he says, how come you're not using two fluid? Okay, so you can use two fluids in the following case. There was a core size which was psi. If you want to resolve that, please stick with Gross-Pidevsky. At least if you're doing weakly interacting Bose-gas. Itamar will tell me Gross-Pidevsky is not helium. He's right. But at least for weakly interacting Bose-gas, we have complete control numerically. Now, if you want to look only at the vortices without worrying about what's happening inside the cores, you can use the Vortex model which he showed you, which is the Biot-Savart, and probably finally use something called a local induction approximation and so on. If you no longer want to remember that the vorticity is quantized, then you come up with a situation where you have many quantum vortices rotating together of the same sign. Then eventually you can extract from it. This is a calculation you can't do. You can only do it verbally the way I'm doing it. Okay? You can't do it on a piece of paper. Okay? Then you get a vorticity field. When you get a vorticity field, then you say, well, I know everything about two-dimensional Navier-Stokes, which I have written here. I think Prasad used these vorticity stream function way of writing it. So that's a vorticity, that's a stream function, that's the velocity. Okay, this is 2D Navier-Stokes with some external friction put in, say because of air drag or something. All right. Now, when you have this two-fluid model, it goes back perhaps to Landau, Tisa, and then the four people here. You have one equation for the normal fluid, that's conventional Navier-Stokes, conventional kinematic viscosity, friction, some mysterious force which I am leaving here called MF, stands for mutual friction. You will remember that from Itamar's talk, and some external force. Similarly, for the superfluid, you write down the same type of equation, and of course you will tell me I'm completely stupid because I put in a viscosity here. But if you do numerical simulations, you have to be stupid for stability reasons. So in any numerical simulation, typically you will have both, with this as many orders of magnitude below this as your numerics will allow. Okay. Similarly, that's a friction here. And then this mutual friction term, which says that one fluid drags on the other, and that's the formal equation for it. You will remember some of this from Itamar's talk, I hope. There were true, oops, sorry. Horrible. So, okay. Now, for the practical calculations I'll give you today, we have set one of them to 0, but we have checked that without that equal to 0 also we can do the same thing. So we have normal fluid, superfluid, pseudospectral method. What are the typical things people calculate? We are forcing it with a Kolmogorov force. That's only for the experts. Basically, it tells you some cosine forcing at some injection scale. So K injection is the wave number at which energy is being put into these two fluids. Okay. So like all people in classical turbulence now, we calculate energy spectra, various transfer functions, dissipation. This is really for the experts. So don't worry, if you don't like transfer functions, ignore it. But this tells you this is the thing that will, they're all defined here, okay, in terms of various things. But let's just look at some data. So we've done many, many runs. Again, limited resolution because we want to explore a large region of parameter space. So what are the important parameters? There is the ratio of the normal fluid to the full density, rho n over rho. So that's this normal fluid fraction. That's one of the mutual friction coefficients. There are viscosities, injection scale, so on. You can calculate all standard quantities. Now, it is generally said that there is this locking phenomenon, that the superfluid gets locked to the normal fluid gets locked to the superfluid. So here's the pseudo-color plots of the vorticity, normal and superfluid, illustrating that. But the movie I'm going to show you is more interesting. The top two panels, there is no mutual friction coupling between the two fluids. The bottom two panels, there is a mutual friction coupling. So you'll see the top left one will freeze because the normal fluid Reynolds number is too high, too low to have turbulence, whereas here the normal fluid will get churned by the superfluid because of the mutual friction coupling, and then these two things will get aligned. The normal fluid velocity and the superfluid velocity will get aligned. So we can look at energy spectra. This is the fluid without any mutual friction coupling, and the moment you put in mutual friction, the superfluid and the normal fluid, the green curves, get aligned. You can look at, this is the first time I think the inverse cascade has been studied in this model in 2D. That's the forward cascade, the inverse cascade, which Prasad told you about in his talk. And this power law in the forward cascade regime depends on the friction, but now it depends also on the mutual friction. And it's not something pretty. You just have to do various calculations, and this number changes. It's not universal, but you can. Sorry?
The problem is not the power.
Well, it's probably a power, but. But that happens all the time in 2D turbulence with friction. I know it's sad but true. Okay. Okay. All right. So you can also explore the dependence on the normal fluid fraction, and again you resolve the two, inverse and forward cascades. But okay, things depend on powers. I won't do the fluxes. That's too technical. Let's just look at the alignment. What do we mean when UN and US are aligned? We can look at the PDF of the cosine of the angle between them, the strong peak at cosine theta equal to 1, so they're aligned, but they're not completely aligned. That gives you with what probability they're aligned. What's more interesting, which has never been noted before, is if you take the ratio of their moduli, let's call that gamma, then there are power laws in the tails of that distribution which are best seen by looking at the cumulative distribution function. I don't understand these tails, but they're there. And as far as I can see, nobody has noted that they're there and seem to be universal, meaning the powers here are the same for all the different runs that we have looked at. Okay, so here's a quick summary. We have analyzed homogeneous isotropic superfluid turbulence in the 2D HVBK model. We've resolved both inverse and forward cascades, and various things depend on the parameters that I told you. So with that, I thank you for your attention. Yes?
Well, just as a comment, I mean, everything
Right.
you say is fine, just a comment that when we really want to understand the fluid, you have to go also to what happens in smaller scales.
Yes.
To the interaction between the complex vortices.
Right.
Then new order parameters have to come in, like brightness,
Yes.
down, so on. So the world still doesn't know what's ahead. It's an open problem, and I think very interesting one, in which one needs to really go and understand how to write the two-fluid model corrected for.
You mean this two-fluid model or the one that you talked about?
Either,
Sure.
to take into account what really happens in the small scale.
So then you might as well go all the way to Gross-Pitevsky if you're not wedded to helium.
As you said, it's
Isn't
not
it?
limit. It's not really.
Sure, that's true.
A proper discussion.
Yeah.
But this whole.
So short of, right, short of doing quantum Monte Carlo or quantum molecular dynamics, even worse. Okay, fine. Thank you.